안녕하세요. 김영섭입니다.
네, 잘 들립니다.
네, 잘 들리시나요? 제 슬라이드 한번 공유해 볼까요? 잘
예,
보이시나요?
네, 슬라이드 부탁드리겠습니다.
안 보이네.
호스트가 화면 공유를 비활성했다고 나옵니다.
네, 잠시만요.
이거 식단 눌러야 되나요? 네? 이거 눌러야 되나요, 이거?
저희 건 안 돼요.
어떻게 안 보이는데? 몸이 스피드는 안 보이는데?
네, 한번 다시 부탁드리겠습니다.
네. 안 되는데요?
워딩 되는데, 예, 제가 이제 들어가겠습니다. 잠깐만요.
네, 죄송합니다. 다시 부탁드리겠습니다.
네. 네, 보이시나요?
네, 잘 보입니다.
네, 마우스 커서도 보이시고요.
예, 커서 보입니다.
네, 예, 그러면 잘 된 것 같습니다.
네, 감사합니다.
네, 그러면 이따가 시간 저는 휴식 시간 다음이니까 휴식 시간에 들어오면 되겠네요.
예.
네, 알겠습니다. 감사합니다.
근데 그 부천 영화제 얘기해요, 사람.
그게 무슨 소리야?
사람 구한대면서.
구하고 있어.
그러면 어떻게 될지 모르니까요.
근데 필요할 것 같아. 한 명 정도? 네, 수성님, 마이크, 카메라 테스트 부탁드리겠습니다.
들리세요?
네, 들립니다.
보입니까? 보이세요?
대표님 말이 안 들어가는 것 같은데.
뭐야, 이게 마이크가 안 되는 것 같아. 들리십니까?
네, 소리 들립니다.
지금 화면 공유를 해놨는데 공유 화면
네.
보입니까?
네, 공유 잘 됩니다. 혹시 전체 화면 가능하실까요?
지금 저는 전체 화면은 보이는데,
네.
지금 보이는 게 PDF 파일로 보이는 거예요?
네, 지금 PDF 그냥 화면 창이 보입니다. 그 화면 공유해서 고급 가셔서 한번 해보시겠습니까?
잠깐만요. 예. 이게 안 되는 거잖아. 오전에 그거라도 하라고. 이거 지금 보이세요?
지금 공유 안 되어 있습니다.
어제 전달해준 그
응.
교수 강의 자료 다 받아냈죠?
우리가 들어?
응?
우리가
오늘
들어?
혹시 모르니까 가지고 있어.
여기.
우리가 공유하고 있어.
우리가. 지금 공유 저희가 한번 시도해 본 거거든요. 혹시 안 되시나요, 공유? 네, 지금 잘 됩니다.
지금 전체 화면이 공유되고 있습니까?
예,
네.
전체 화면 잘 되고 있습니다.
넘기려면 반응이 늦네.
조금 느려가지고.
이게 넘어가고 있습니까?
네, 넘어가고
네.
있습니다.
예, 감사합니다. 조금 이따 뵙겠습니다.
네, 감사합니다.
네, 소장님, 한 가지 더 말씀드릴 게 있는데요.
네네.
네, 그 Q&A 시간에는 카메라도 조금, 카메라 한 번 더 켜주세요. Q&A 시간에는.
지금 카메라
같이.
안 켜져 있습니까?
이게 끝나고 나서 Q&A 시간이 있잖아요.
3시 15분부터.
네네네. 그때, 비디오를 끄지 마시고,
예.
네, 비디오를 켜서 이렇게 얼굴이 보일 수 있도록 좀 진행 부탁드릴게요.
알겠습니다.
네, 감사합니다.
네.
네.
그리고 진짜 편하네.
그러니까. 이거
봄이 봐. 이거
사투리 너무 심한데, 나?
네, 호스텔은 기분 좋다.
여기에 지금 계속 중계가 되고 있는데.
우리 한 거 다 지금 나가고 있어. 근데 뭐 어쩔 수 없었던 거.
이게 안 켜져 있어서. 그래서 오늘 몇 분이에요?
그래서 끝났어.
한국 사람.
그냥 그분 아까 하신 거, 맞네요. 근데 세 분인데?
그렇지, 세 분이지.
되게 잘 들어오는데 시간 좀.
So, good morning. Good morning from India. Hello. I am Bhanu Shankar Rao from INAE. I am the chair.
이거 해서 안 들려.
I am the chair for the first session today.
Hello, nice to meet you. Nice to meet you, Professor. So we have to cracking system. So first, speak system first. I hear. Speak again, please. 나가버리네. 그래. Professor, can you hear me?
Yes, I am able to hear you.
Oh yeah. Okay. It's
are you
speak
hearing me?
system. Yeah. Good. Working now. Yeah. Mic system is working now. And second function system is check it out. Do you have a file? File? Do you have your file, Professor? Hi. 이 사람 왜 이래? handsome. 아이씨, 안 들리나 본데? 연결이 안 돼요. 연결 상태가 안 좋은 것 같다고요? Hello.
Hello.
Yeah.
Yeah.
May I check out about your presentation file?
Oh no.
Can you show me?
I don't have the presentation. I am the chairman of the session. Okay.
없을 수도 있다고. Yeah, okay, I understand that. The second, I will check about the presentation. When you have a presentation time, full screen, okay? You make full screen.
Yeah.
Okay. The second, when you have Q&A time.
Yeah. Carry on.
Hello.
Yes, please carry on.
Yeah. Second, you have to when you have Q&A time, you click the video start.
Yeah.
Okay, video start button.
Okay.
Okay, you understand that?
Yes. Okay.
Okay. 이 사람은 이거를 파일이 없다고요?
네, 꺼졌어요. 네, 잘 끝나셨어요? 네, 식사하셨나요? 아, 예, 맛있게 드십시오. 어떻게 하기로 하셨어요? 아, 그래요? 그 드롭박스로? 아, 그래요? 알겠습니다. 네, 그렇죠. 뭐, 다 사람도 안 오는 거였죠. 몇 명 안 오고. 네, 그냥 뭐, 네. 아, 그래요? 네, 고생하셨습니다. 아침부터. 네. 아, 또 알아보네요. 확실히 영어한 사람들이라서 그런지. 몽타주 충돌 기법을 안 해요. 이따 치킨 시켜서 같이 저거 하시죠. 이 PK 편집하시죠. 네, 알겠습니다. 연락드리겠습니다. 네.
가수 선생님.
네, 그렇죠. 바수.
네.
바수 테스트 하시죠.
네.
마이크 켜주세요, 마이크.
예. Hello, Professor 바수. Hello.
가수 선생님 마이크가 안 켜져 있어요.
바수 들었어.
Hello, nice to meet you, 바수 Professor.
초록색. 이 초록색 안 빠지는 게 신기한데?
Hello, good morning.
Can you hear me?
Yeah, hello.
Yeah. Nice to meet you, Professor.
Yeah,
So, I need to check out your function system, connecting system. First, you hear me, okay? Very well? You hear me very well or not? Hello?
yeah, tell me, I'm not
Oh,
able to.
yeah, you got it. Okay. Okay. Speaking system is good. It's second function check. I need the second function. So you got a file system, presentation file. You have it. Hello.
Yeah, I'm sharing that.
Can you show me your file, please? Okay. Okay. That's good. Okay.
Okay, thank you.
Yeah. And full screen 됐잖아요. Please full screen, please. Full screen, please. You make full screen, please. Okay, thank you. Yeah. Okay.
Okay,
Yeah.
thank you.
Yeah. Your presentation time is you use the full screen, okay?
Yeah, I'll do that.
Okay.
Thank you.
No. Not the ending. I want to check it out the next function. You have when you have a presentation time, you have to make full screen. Okay. Second, when you have Q&A time, in your make click the video start button. You understand that?
Yeah,
Okay, thank you. Make your full screen, please, right now. Can you make it full screen, please?
yeah, just 1 second.
Yeah. You have some problem now?
Yeah, just 1 second.
Okay. 1 second.
Slow.
전화 왔어요. 예?
아니, 다들이 하셔도
뭘 정리해? 이거 정리해 달라고요? Okay. Your presentation file is working. So, can you close your file, please? Please close your file. Okay, thank you. 이분 됐고요.
인도사람 분명히 아직 안 왔어요. 온다고 하는데 만약에 너무 오시고 늦게 되면 오실 것 같아요.
예?
지금
네.
오픈도 안 나갔어요. 이제.
예.
신발을 내니까 한국분은 그냥 안 하고 전화로 슬라이드 보면 진짜 떼고 나중에
kemarin cuma kita sih problem.
그 다음에는 이렇게 하면 안 돼요. 이게 이렇게 튀어나오면 무슨 예를 들어 이렇게 링크 이어가는 걸 안 보일 수 있게 그 이어서를 다시 들어오면 풀면이라고 하고 자기가 이제 같은 회의하는 거야. 회의할 수 있는 거니까 TV가 없고 그렇게는
라면 상크라 매우 코타. 이것도 이분 들어오신 거예요?
그분이 자장님이시고요.
자장님.
네.
그럼 두 분 들어오셨네. 나머지는 아직 안 들어오셨고.
두 분? 네, 그렇죠. 가수 선생님이랑 자장님 하셨으니까.
그렇죠. 예.
그리고 이제 두 명의 연사가 더 들어와야 돼요.
그래요? 아직 안 들어오셨고.
네.
한국 사람 한 명이랑
예.
인도 사람 두 명 아직 안 했다는데요?
네.
맨 마지막 한국 사람
혹시 밥 먹었어요?
네.
저는
왜 안 들어오시지? 기록되고 있다고? 동의해야 되잖아.
기록되고 있어요. 저희 호스트 기록
근데 갤러리가 하는 말씀하시는 거예요?
테스트부터 연결한 것 같습니다. 네, 10초 정도였을 거예요. 네, 감사합니다.
어제 녹화한 거 확인해보니까 채팅창 안 보이던데.
괜찮아요. 안 보이면 좋죠.
없어.
네. 1시에 그냥 바로 시작할게요. 네, 끝내요.
삼 분 남았네. 오세요. 응? 이 들어온 것 같은데요, 수아씨, 조씨?
1시간 없을 것 같은데요?
예?
1시간 없을 것 같아요. 공지만 해주세요.
Good morning. Are you able to hear me? Good morning.
Yeah, good afternoon, Korea.
Hi, good afternoon. I can hear you.
Yes, yes. Can we start the session now? I'm the
Yeah.
chairman.
You're the chairman. You can chair it.
Yes. I am Professor Bhanusankar Rao from University of Hyderabad, School of Engineering Sciences and Technology. I am fraternity chair professor at University of Hyderabad now. Today, we join the session on additive manufacturing, where there will be 6 presentations. Can I continue now? Hello.
Yeah.
Yeah.
Good morning.
Good morning to.
Am I audible?
Yes. Vikramjit? Yeah, you're audible. Before
Am I
start,
audible now?
yes, you're audible. I will come back to you. I will briefly give introduction for a couple of minutes and
Hello.
then you to present your talk.
Hello.
Yes, Vikramjit, we are able to hear you. Yeah, in the recent past, manufacturing of industrial products has undergone revolutionary changes due to emergence of I2 manufacturing. I2 manufacturing offers the flexibility in designing various components. Over the next 10 years, AM is expected to transform from production of parts to production of systems. In order to ensure the structural integrity of the systems, AM parts shall be sound and free from the microstructural inhomogeneities and critical manufacturing defects. AM parts in as-built state exhibit high residual stresses, complicated microstructures, high surface roughness, porosity, inclusions, texture anisotropy, and mechanical properties that are dependent upon the process variables employed, feedstock material, and by the composition of the alloy. There is an urgent need for scientific interventions to provide solutions to several of these problems and developing mitigation technologies to minimize the geometric defects. Among the several mechanical properties, the resistance to creep and fatigue at elevated temperatures act as the critical indicators of component performance in the applications foreseen for AM parts in gas turbine. The evolution of creep and fatigue properties has not received much attention. The appropriate heat treatments and hot isostatic pressing can give full play to the potential of AM parts built from superalloys and can ensure the service lives equivalent to or better than conventionally manufactured alloy of similar composition of rod parts. With this brief introduction, I invite Professor Vikramjit Basu from Indian Institute of Science, Bangalore, to present his talk on ultra-high temperature ceramics for aerostructural applications. Professor Basu is currently a professor at Mittal Research Center, Indian Institute of Science, Bangalore. He is also an honorary professor, University of Manchester, UK. I invite Vikramjit Basu to present his talk. Basu, unmute. Basu has to unmute. Vikramjit, you have to unmute.
Is it, am I audible now?
Yeah, we are able to hear now.
Yeah. So good morning, everybody. First of all, I would like to thank the organizers and in particular, President of Indian National Academy of Engineering, Professor Manna, Dr. Bhanu Shankar Rao from Indian National Academy of Engineering, as well as Korean National Academy of Engineering to invite me to present this talk at this bilateral symposium. So the title of my talk is Ultra High Temperature Ceramics for Aerostructural Applications. This is the work I have started at when I was a faculty member at Indian Institute of Technology, IIT Kanpur during 2001 and 2011. And later on, when I moved to Indian Institute of Science, Bangalore in 2011, I still continue this work and in collaboration with BrahMos Aerospace in India. So the plan of my talk is that first I'll briefly introduce that UHTC because most of the talk in this symposium is largely on the high temperature metals. Then I give you some illustrative examples to show the development cycle of two representative borides, that is zirconium diboride and niobium borides in our group over last decade or so. At the same time, I'll also show you some of the results where I'll illustrate how to combine computational analysis with the experimental work to develop an overall understanding on the performance qualification for this UHTC for hypersonic vehicles. And finally, I give you some brief introduction to additive manufacturing of ceramics and some startup activity in India and concluding remarks. So UHTC is typically characterized by very high melting point over 2,500 or so, and in those kind of ceramics, it is expected that the room temperature properties are largely retained at high temperature. And when I say ultra high temperature ceramics, their microstructural stability at mid to high temperature is advantageous over other classes of ceramics, like several other oxides, for example. Now, what are the challenges? Challenges is that how to develop, how to consolidate extremely dense sintered components with good strength reliability, as well as meeting other performance criteria. The reason being so that that various additives are added to these ultra high temperature ceramics during consolidation process, and that lead to sintering reactions. I'll show you some examples of that. And then high temperature mechanical property measurement facility often becomes a bottleneck, because many academic institutes often do not have these kind of facilities where you can measure the strength and other performance limiting properties at a temperature above 1000 or 1500 degrees Celsius. So UHTC is generally defined as a class of ceramic materials, particularly borides, nitrides, and carbides, which are made up of the transition metals like zirconium, hafnium, niobium, tantalum, for example. So these are the two particular phase diagram I'm showing you, just to show you that what I'm going to show in next 10 minutes or so is that zirconium diboride system. In the ZRB system, if you see, zirconium diboride is almost a line compound, which is a stoichiometric composition of around 66% boron, and a melting point is above 3200 degrees Celsius. Another materials I'll also show that we have developed is niobium diboride, and here niobium diboride is not that much, is strictly speaking not a line compound, and it has a melting point is over 3000 degrees Celsius. So these are the two materials I'll show you in next couple of minutes. Now, before I move on to my scientific presentation, let me also show you some of the what is the current status of ultra high temperature ceramics research around the world. So here I have mentioned some of the representative groups. By no means this is this represents the complete spectrum of the active researchers who are working in the field of ultra high temperature ceramics. So if you see in this group is that in this global landscape, there are number of groups both in United States, North America, Europe, and Asia. They're working in the field, and particularly it is important to mention there are significant activities in NASA and European Space Agency, but most of the reports are unavailable in published literature. While looking at the present status of the literature, we have found that although there are significant experimental efforts, but there are limited efforts towards combining computational analysis with experiments to design thermal protection system. Now, having said that, let me show you that what is the national landscape, particularly ultra high temperature ceramics in India. Again, I tried to put together some of the important groups at different Indian Institute of Technologies and national labs, space, ISRO labs, Indian Space Research Organization labs, as well as some of the NITs, National Institute of Technologies in India, where people are working on different types of ultra high temperature ceramics like hafnium diboride or zirconium diboride based materials, or some of the work is going on also in the titanium diboride based materials. Now, what is the relevance of this ultra high temperature ceramics in the overall aerostructural applications? So this is the generic image of a hypersonic cruise vehicle. Now, if you see the leading edge and the wings and then sharp nose, these are the places where temperature is expected to be very high, or more than 2500 3000 degrees Celsius. So there you can, these materials are most suitable candidates. And this is the leading edges, which also experience severe aerothermodynamic conditions in temperature of high pressure and heat flux. And all the current materials which are used, like ceramic matrix composites or reinforced carbon-carbon composites, which has a temperature capability of 1650 degrees Celsius. And better choice, we believe, is certainly ultra high temperature ceramics, where it can sustain the temperature of more than 2000 degrees Celsius. Now, when I started this research, the first thing we did a lot of this computation analysis just to rationalize the selection of the materials in our research. Now, in this particular computation analysis, what we call is a coupled thermostructural analysis. So essentially, we analyze, we use the CFD code, computational fluid dynamics code, particularly 3D Reynolds average Navier-Stokes equations with Spallard Almaraz turbulence model. Now, the output of this computational analysis, particularly pressure and heat flux, is taken as the input to the structural domain and to find out what is the von Mises stresses or principal stresses, as well as the displacement that the component is expected to experience under such severe aerothermodynamic conditions. So in our computational analysis, we have considered the Mach 7 cruise speed and 2.1 kilometer per second, 30 kilometer altitude and 500 kilometer range, and cruise time we have taken as 250 seconds. So this is a little bit more details about what are the kind of structural meshes that we have considered. I would like to mention here that we have used that hypermeshing just to ensure that high fidelity solution also can be obtained, and it is particularly 20-node hexagonal structural element. So this is a little bit more details about the coupled thermostructural analysis that I have talked about one slide ago. And then here we have solving that finite element code here, and also this is the thermal domain which is used in the thermal evap in the finite element analysis modeling. Now, what is the results we have got? Now, if you look at this normalized distance from the leading edge, it is at the leading edge, the temperature at this particular aerothermodynamic conditions is expected to increase more than 1200 or 1200 to 1400 Kelvin. And this is the maximum principal stresses. If you see, maximum principal stresses can go up to as high as 100 megapascal or so. And that in the maximum principal stresses is around 166 megapascal, and maximum deformation is 0.6 millimeter. And if you consider von Mises stresses, it is around 35 MPa that the titanium or underlying metal would experience. Now, as I said in the introductory part of this presentation, that consolidation on sintering presents a serious challenge for these materials. So we have used spark plasma sintering, and since it is a Korean National Academy of Engineering also is one of the organizer, I must say the spark plasma sintering technique I started using when I was visiting Professor Do-Yeon Kim's group at Seoul National University in the year 2002. And thereafter, I have developed this facility in India, or I have installed this facility in India at IIT Kanpur, and it still remains there. So in this spark plasma sintering technique, what we use multi-stress sintering technique, like that we hold it at a temperature which is around Tm by 0.5 Tm. Then we increase the temperature, we hold it at secondary holding temperature, second hold, and before it reaches the final sintering temperature. And we have investigated that this kind of three-stage sintering or multi-stress sintering process essentially allows one to control the grain growth, at the same time enable the achievement of the very high sinter density. Now, this is the zirconium diborate-based materials with silicon carbide as the reinforcement, and also titanium disilicide as a sinter aid. And when we have developed, we have found that there is a very tabular shaped zirconium diborate grains, and also this titanium disilicide is also dispersed in the microstructure very finely. In terms of fracture toughness and fracture resistance of these materials, now we have obtained that modest fracture toughness values K1C when we have measured it in single edge V-notch technique up to 4 MPa square root meter when you add this 10% of the sinter aid, and then viscous hardness is roughly around 30 gigapascal, which is quite good in this kind of ceramics. So as next step, we have developed these very recently. We have developed these niobium diborate-based materials. Again, following the similar processing strategy, here we have adopted forced sintering technique by holding this niobium boride, which has been milled with the zirconia milling media at different temperature up to 1750 degrees Celsius. And if you see this array of the transmission electron microscopy images, you can see hexagonal niobium boride is retained, and we can see a lot of defect structure in terms of twins, stacking faults, and so on. And interplanar distance that we have measured as around 0.325 nanometer. So essentially, what I would like to show you in the next slide is that this defect structure allows us to understand that what is the core mechanism of the densification in this niobium diboride-based materials. So in the spark-transfer sintering, there is something called constriction resistance. Like when the current is going to pass through the different particle boundary, so it experiences certain resistance, and this resistance can be theoretically calculated by this kind of expression, whereas RC is the constriction resistance and rho is the average resistivity of the sample, and ever is essentially average particle size in the cluster, and alpha is the size of the cluster. Now, we have done these simple calculations to find out how this constriction resistance also reduced with more number of contacts in this particular niobium boride zirconia system. Subsequently, we have done some calculations about the activation rate of the diffusion, and we have found the pipe diffusion is, as expected, is much higher than the other diffusion mechanisms in these kind of systems. Now, taking it forward, we have developed niobium diboride-based composites with boron carbide as a second phase addition. And this boron carbide second phase addition, when we added a different amount like 0, like 10, 20, 30, and 40%, and we have seen around 20 to 40% addition of boron carbide, a new intermetallic phase forms, which is a composition of niobium 0.85, zirconium 0.15, boron 2. And the formation of this particular intermetallic compound can be explained by sintering reactions, which has been shown. Unfortunately, we could not do thermodynamics analysis to show you that delta G is negative for these particular sintering reactions, but we certainly believe this is what the sintering reactions takes place. Since it is a new intermetallic phase, we have used some of the state-of-the-art technique like atom probe tomography, trying to see in this particular intermetallic phase what is the distribution of niobium, zirconium, and boron. And based on all this transmission electron microscopy and selected area diffraction pattern and APT based analysis, we have found out that this could be the possible crystal structure of this niobium 0.85 zirconium 1.5 boride compound. Now, coming to the performance qualifying assessment of ultra temperature ceramics, we have used different type of testing. This is the first one is RJ testing. This we have done at Indian Space Research Organization, that is at Trivandrum. So this RJ test essentially was carried out with a heat flux of 2.5 megawatt per square centimeter and with exposure time of 30 seconds. So if you see this, once this arc is heating, this is the material which is exposed, and this is how the material is mounted at the arc jet testing chamber. And then we have done some computational analysis to find out that what is the back wall temperature. By putting the thermocouple at the back wall, we can extrapolate that what could be the front wall temperature which is exposed to this arc jet. And then this is how the temperature time history you get from this finite element analysis, and you can see that at the very front wall temperature can be very as high as around 1200 Kelvin. So this essentially our UHTC is exposed to this kind of temperature and aggressive heat flux conditions during the RJ testing. So what is interesting to see, when we have looked at the microstructure of these materials, we have found very much dendritic type of microstructure, which is typically people observe after solidification of metals. And you can see primary dendrite spacing as well as a very nice development of the secondary dendrites and so on in these RJ tested zirconium boride materials, which essentially tells us that locally this material is melted and subsequently solidified. And this is how this RJ tested sample, that exposed sample appears after testing for 30 seconds. Now, second performance qualifying tests that we have done is a high temperature erosion test. Now, in view of the limitation of the experimental setup, we could not do at temperature above 1000 degrees Celsius, but we have done at the temperature of 800 degrees Celsius of the 50 millimeter diameter sample. And as I said before, that we always combine that computation and experiments together. And this is the and this is the results of the finite element model, and to show you that what is the stress level here. Remember, this is 10⁷ Pascal. So it is like you have to see the 10 megapascal multiplied by 4.9. So almost like 50 megapascal stresses that is being generated around the erosion crater or around that erosion crater in the two different type of materials that we have investigated. We have also utilized that Oka erosion model, where we have found out that what should be the erosion rate of the theoretically predicted erosion of the composites by getting the experimentally measured values at the normal impingement angle, what is E90. So V and V reference are the impingement speed like 50 millimeter per second, and reference velocity is 104 millimeter per second, and all of the parameters are mentioned. What is important to mention here that following the Oka erosion model, what is the theoretically predicted erosion rate that closely matches with the experimentally measured erosion rate, at least in this case of niobium zirconia composite, niobium zirconia composites. Now, when you have investigated that as eroded surfaces, we have observed a couple of interesting things. One is this grain pullout and flaky exfoliation, and apart from this, instead of tetragonal zirconia, we have found orthorhombic zirconia, which is present on the as eroded surface. We went ahead and further find out that what is the how this NB2O5 also forms because of the oxidation during that during the erosion, and what is the dislocation activity and the as eroded surface. We have found that after 800 degrees Celsius temperature testing, there is significant dislocation activity on the as eroded surface. That is very clear from that HRTM image. This is the third and last one as far as the performance qualifying test is concerned, and this is what we have done at our Center for Excellence at the Hypersonics at Department of Aerospace Engineering of Indian Institute of Science, and we have used that free piston driven shock tube. So essentially, you pull this 20 kg steel piston in the reservoir. Now, once you release this piston, it will boom in this aluminum diaphragm. This aluminum diaphragm is burst, and then after rupture, it is like this. And then after that, this shock wave travels to this shock tube, and then impinges or impacts on the zirconium diboride or niobium diboride, whichever you keep it at this flag at this end of the sample. So by putting different pressure gauge, you can essentially monitor that what is the pressure being generated in this shock tube, and then you can essentially calculate that what is the expected temperature increase by certain theoretical calculations. Now, this is the typical pressure pulse this material is experiencing over a period of few milliseconds time frame. And this is what we have calculated, that what is the initial test gas and what is the incident shock gas pressure. And from there, we can find out that reflected shock temperature is over 4000 Kelvin. So that is very important to keep this in mind. But remember, this material is experiencing this kind of shock pressure over a time scale of few milliseconds, like less than 5 milliseconds. Okay, now we have we have done further this hypersonic shock test in the zirconium diboride based materials. We have found out very few nodules of the zirconia which are present after the exposure, and then we have subsequently done X-ray photoelectron spectroscopy analysis just to show you that it is the zirconium oxide which is present, but this zirconium oxide is essentially a result of the oxidation of zirconium diboride, but their presence is not very, very significant, I must say. We have also extended our niobium diboride work, and then we have used detonation-driven shock test. So this is a little bit miniature model, not like high-pressure shock tube model. And while using this particular test facility, again at Aerospace Engineering Department of ISC, we have modeled this, what would be expected temperature and pressure at this shock at the shock material interface, and what will be the total heat flux. We have solved this conjugate heat transfer modeling, And what you find at the rim, there is a temperature increase of more than 900 Kelvin, and then total heat flux can go up to 3.3 into the 7 watt per meter square. Now, interestingly, in case of
Yeah,
2 minutes. Yeah, 2 minutes. Yeah. So I'll just keep it. So now I'll move on to the 3D printing of ceramics. So this is what we are planning to do. We are planning to see that whether zircon diboride and some of these ultra temperature ceramics can be printed using 3D printer. And this ceramic 3D printer is based on the principle that you can essentially utilize, you can mix this photocurable resin with the powder, and then you can find, and then you can cure it, and then you can do layer by layer deposition. So this particular company, 3D Ceram France, they have shown that this particular printer can be utilized to print the different components for space propulsion systems or mirrors for optical applications, as well as the antenna for nano satellite applications. So this is very unique, but what is the crux of this technology is that what is the composition of the photocurable resin. So before I conclude, I would like to mention that there is some activity in the private defense startup sector. So this is India's one of these very fast private defense startup in the hypersonic glide vehicle domain, and this is HTNP Industries. So they would like to develop hypersonic glide vehicle by combining the advance of a cruise and ballistic missile, and they are working on that more from the design to essentially materials innovation. So these are the two important pillars they are looking at. One is the aerodynamic design, and second one is the material system. And this is a very ambitious program. They are planning to develop material system with a Mach number of 15 or 15 plus. So this is the core team of the people who are working at this particular startup. They're a very young group of people who have different expertise or widely different expertise, right from electronics to systems engineering to material science and so on. I'd like to acknowledge my past and present collaborators, Professor Do-Yeon Kim, who was formerly at Seoul National University, Korea, and several other people in India, as well as my alumni who has worked in this particular engineering ceramics, and they are currently faculty at different IITs or NIT in India. And subsequently, I would like to acknowledge the funding agencies like Department of Science and Technology, Atomic Energy, DRDO, and Indian Space Research Organization, BrahMos Aerospace. And Hamsamida, thank you very much.
Thank you, Basu, for your excellent presentation. We'll have the question and answer session later. I will invite the second speaker of the morning, Yung-Gyo, Principal Research Engineer and the Team Leader, Advanced Material Design Team, Hanwha Aerospace R&D Center, to present his paper on present status and future prospects of additive manufacturing for gas turbine in Korea. Yeah, you can start.
Yeah, please, just one moment. Can you see here?
Yes, yes.
Yes, I will start my presentation. Hello, this is Yung-Gyo. I'm the head of the material design team at Hanwha Aerospace Research and Development Center. First of all, I'm grateful to be able to present at the workshop of Korea, India's scholar. What I will present today is the current status and the future perspective of Hanwha's gas turbine engine 3D printing technology. Yeah, as Hanwha Aerospace is a defense industry company. Therefore, presentation material must be comply with the national security. Please understand that taking photos or recording video is not permitted. Yeah, this is the today's presentation's content. I would like to briefly introduce the market trend, basic 3D printing technology, global trends, and finally Hanwha's current status and the perspectives of 3D printing technology. This slide shows the AM market in the aerospace industry. With 3D printing, compound annual growth rate of the aviation industry is expected to be about 21% over the next 11 years. By 2029, it is expected to be around the $7 billion. Yeah. This rise of technology perspective of aero engines. As you know, recent technology perspectives of aero gas turbine are eco-friendly, high efficiency, and manufacturing innovations. The global OEMs designed a combustor that minimizes carbon and nitrogen leaks for eco-friendliness. Increase the fan size and reduce the weight by applying composite material to improve the performance. And finally, introduced a smart factory for manufacturing innovations. 3D printing encompasses all three of these technologies. Yeah. The development of the complex shape of a turbine nozzle using the 3D printing reduced the carbon dioxide emissions by the complex design and the aero nozzles. And the titanium aluminide composites, the low pressure turbine blade developed by 3D printing has improved the engine performance by reducing the weight compared to the existing incarnate. Lastly, the production of the complex case or turbine case structure with the 3D printing shortened the development schedule, delivery time, and simplified the development management compared to the process of the welding, casting, and forging. This chapter introduced the AM development procedure from the design and the qualification, and the major product manufacturing process for aero engines. This slide shows the development processes for aero engines. AM development processes starts with the material design and the shape design. Found materials or process powder bed fusion or direct energy deposition process, and the 3D printed parts shall be qualified and approved by designer authority with the verification of design intent. This is the procedure required by the US FAA and the European EASA's airworthiness regulations. It is very important to keep in mind this procedure. I'm sorry. Yeah. This slide shows the major development process, powder bed fusions, and the DD process. AM development processes start with the engineering design. Also, introduced this slide, two major 3D printing process applied to the development of aviation's gas turbine engine. Powder bed fusions process is suitable for passenger parts such as the blade and the nozzle, which is important to the precision and the excellent surface roughness part. On the other hand, the DED, direct energy depositions process is suitable for repair parts such as the large compressed case, whereas the other the turbine case. And these chapters introduce the development of status of the Grover's OEM. First, currently, GE is a global leader in the world and is expanding the application of the 3D printing parts after the development of the catalyst engine, which they will finish the flight test 2021. The part in the picture of the on the right products developed and applied by 3D printing in catalyst engine. The main development goal through the application of 3D printings are to reduce the engine weight by 5%, introvert 855 12 parts, and the shorten the development period by more than 6 months. GE also established various databases for design and life evaluations while developing 3D printing fuselage for LEAP engine. The figure on the right highlights the steps required to generate the fatigue strength. As shown in the figure, in order to generate a minimum design barrier, must be considered the deviation of the data point minimum work property and consider the environment deviates and the surface roughness physical feature deviate. Therefore, designer can get the positive margin in this point. It is very important to generate the design allowance by this kind of the 3D printing process. Rolls-Royce is also developing 3D printing parts, titanium, 6 aluminum, 4 vanadium bearing housing, which is applied to the XWB 1997 found engines and establishing design data. Pratt Whitney also developing various engine parts. It can be seen that Honeywell, a strong player in the small gas turbine engine field, is also establishing a lot of data design for and life evaluations by developing engine ductors, the rear engine duct. Safran, the French company, has also established the data for design and life evaluation through forward-oriented since the early 2000s. And you can see the roadmap that has recently been applied to engine with this developed material, powder material. Avio, the Italian company, also contributed to reducing the engine weight by about 400 pounds by developing titanium aluminide for low pressure turbine blade for G and X engines. These chapters introduce the history of Hanwha and the 3D printing development status of the Hanwha's aerospace. Hanwha Aerospace began maintenance of the aviation gas turbine engine in 1979, about 40 years ago. After that, it successfully carried out the manufacturing and the assembly business of our F-110 engine. And based on this, it grew into a company export parts for civil aircraft engine, G, and others, the Pratt & Whitney, Rolls-Royce. In addition, Hanwha Aerospace is developing its own engine. This slide shows the Hanwha Aerospace independent engine development history. In 1996, industrial gas turbine was developed by ourselves. Since then, it has developed aero engines for guide weapons and auxiliary power for defense system. And now, currently working on the joint design T700 and KFX engine with G. This slide shows the history of Hanwha Aerospace 3D printing technology development. Hanwha Aerospace started developing 3D printing technology from 2009. In the early days, the bearing seals of F-110 engine was developed using the direct energy deposition process. Since then, shrouded impeller applied to the industrial compressor has been developed, and recently, gas turbine combustor part and the compressed casings are being developed by the wet fusion process. From 2012 to 2014, shroud impeller for industrial engines were developed. Existing impellers are manufactured by machining and electron beam welding, brazing, the final machining. On the other hand, the 3D printing AM parts is the AM building is the finished. After that, development quality was verified through the mechanical property and the metallurgical analysis and the performance testing. After the development, it was presented at the symposium of the Global Mechanical Society. But the final mass production was not used due to the concern about the surface roughness and the force in the area with high mechanical stress concentration. Yeah, from 1992 to 2020, the combustor swirl of the industrial gas turbine F-class was developed by applying the further wet fusion process. After reverse engineering, independent quality verification requirement was established, and the commercialization was confirmed through mechanical tests and the metallurgical analysis. From 2019, from the government projects, the turbine nozzles of the industrial gas turbine F-class is being developed by applying the DFARM and the PBF process at the design stage. Completion schedule is 2023 years. A cooling concept that can improve cooling performance is introduced by using the design flexibility. That is advantages of 3D printing. reverse engineering is currently the progress, and the mechanical test and metallurgical analysis are being performed after manufacturing some small scale parts. From 2018-2019, the combustion nozzle for industrial gas turbine was developed in the hot-bed fusion method. The development process was changed from machining, welding, and brazing to 3D printing. 8 individual parts were integrated to one part. Quality verifications requirement was also designed. Afterwards, a product was developed through the 3D printing process, and the sprite test was performed to verify the flame stability. As a result of the verifications, it was confirmed that the 3D printed part was superior to existing process parts, welding and brazing. In 2008-2009 years, another engine part development was carried out. The development part was the compressed housing, material 15.4 plus the pH material of the gas turbine engine aviations, and the applied process was part of the fusion. In the initial design stage, DPAM design was applied to optimize the printing say through stress analysis. Although the real product development was completed, there was technical difficulty to removal of this kind of support.
Yung-Gyo, you have to conclude.
Yep. Yeah. From 2009 to 2011, 3D printed of 3-stage bearing seal of the F-110 engine was developed. This is the first case of commercial development by applying 3D printing technology in Korea. It was confirmed that the heat affected zone was 6 times smaller than that of the conventional gas tungsten arc welding, which was excellent in terms of quality. For applications, actual engine repair, high cycle fatigue verifications are also performed. It has obtained a final approval from the Republic of the Korean Air Force. And even now, the 3D printing repair process for this part is being applied in the mass production. Recently, also, the Air Force has been commissioned to develop bearing seals for another models of F-100 engines, and the developing is ongoing. By the government project, the target schedule for development completion is 2021. The current basic real product simulation verifications has been tested. For more in-depth study with the Air Force, even dislocation reinforcement mechanism, including high temperature stance and the fatigue property, are being analyzed. Now, let me tell conclusion. This slide highlights the future 3D printing development prospects. Based on the core technology secured so far, we will continue to expand the development of the engine part. This is, and we plan to link with the national development project. Throughout development in collaborations with the powder, process, and equipment companies, we will generate a design, allow stress database that enables design and lifetime evaluation and engines. For final mass production, it aimed to establish a supply chain by securing relevant quality standards in our Hanwha Aerospace standard. This is the final. 3D printing process, AM process, will continue to grow in the aviation industry in the future because it has superior advantages over the existing casting and forging process in terms of QDC. For this, collaboration of the design, building process, post-processing, entity characteristic analysis is very important. Hanwha Aerospace will do our best to commercialize 3D printing parts like global OEMs. Thank you.
Thank you, Yanki. Now I invite Subhas Joshi, Department of Mechanical Engineering, University of Technology, Bombay, to present his paper on generating multi-scale functional surfaces using laser micro machining. Good morning to Joshi. You can present your paper now.
Yeah. One moment, I'm sharing my screen. Am I audible?
Yes.
Thank you. So thank you, Chairman of the session, and my thanks to INI for giving me this opportunity to present our research work. I'm working at IIT Bombay, Mechanical Engineering Department since last more than 20 years. I'll be talking about laser micromachining and generating surfaces with lasers on a micro scale, then micro to nano scale, and from nano to multi scales. I work in manufacturing, so various methods of manufacturing and their applications. So these are some of the examples of variety of the laser developed structures on the surfaces. Most of these are from our work. The other applications of this direct applications include the anti-biofouling on the implants, aircraft winds and turbines for the anti-icing kind of structures, hydrophobic and self-cleaning kind of structures, anti-corrosive kind of structures. So texturing has wide applications. These are some of the parametric details of various recent research, but I would not go into details of this. One of the micro scale texturing which we applied on the cutting tools, especially for machining of titanium alloys. All of us know that titanium being very difficult to machine and a sticky kind of material which sticks to the surfaces of the tool. So we tried a variety of microstructures on the surfaces of cutting tools, and like a simple dimple structures, grooves, structures like long grooves on the surfaces, and then a combination of dimples and grooves on the on the surfaces. And this length over which these textures are made are of the order of 150 micrometers. So this total length, if you see, this is about 150 maximum, 150 to 125 micrometers. In the second case, we have used femtosecond lasers to scan the surfaces in 2 or 3 different fashions, in the way that there is a pulse overlap, that the pulse lasers are overlapped one on each other, and there could be overlap could be 25% to as high as 90%. And then besides the pulse overlap, we have line overlap also. So the first line is overlapped by the second line, again up to the extent of 25 to 75%. And then this can give rise to a variety of micro scale sort of structures. In the third level, we did it something called as the hatching pattern on the laser surfaces, on the work surfaces. So the hatching is H is the hatching distance between the two lines when you are scanning the laser on the surface. And then you go for multiple scans, first, second, third, fourth, as big as 29 kind of scans on the surfaces. And you will find that with the multiple scans, you are able to generate some another extraordinary kind of structures on the surfaces. So I'll go to the first kind of structure. This is dimples, grooves, and dimples and grooves kind of structures. The first effect in the machining process, which you will find, is on chips which are produced. So these are the cross sections of the chips which are generated. You will find that the non-texture tools have significantly high strains. These lines and lines indicate that it's an extremely strained material. And the more the strain, the more the energy required, more the friction, more the tool wear, and everything is high. Similarly, when you take it at little higher feeds, the rate of machining is higher. At that point, you find that the segments are very thick and prominent, and those segments will cause a lot of chatter in the machining process, which can damage the surface finish significantly. But when you use the textured kind of tools, so these examples of dual textured kind of tools, then you will find that even at higher feeds, you have that segmentation has got significantly smoothened because of the textures. Among all kinds of textures, you find that the first line always corresponds to the non-textured tools, whereas the last line corresponds to the dual texture tools. And you can find that in all the cases, forces, etc., you find that there is a significant reduction of the order of 17 to 31% reduction in the cutting forces. Coefficient of friction also reduces significantly when you are using these kinds of dual textured tools. Adhesion get also reduced. So these are the first figure is the tool with non-textured tool, and you find that there is a significant amount of addition of material on the surfaces, and that changes the geometry of the tool. The built-up edge which is formed actually slips over during the machining process, and it spills the particles on the machine surfaces. And so the best one which is surviving in such a harsh condition is the dual textured kind of a tool. I'll go to the next section. I'm just repeating this particular slide of the methodology, where we are doing something called a pulse overlap. that the pulses are overlapped on each other, ranging from 25% to 90%. And then we are doing the pulse overlap and the line overlap. Pulse is along one line and the line second overlap. So the lines are also overlapped and pulse are also overlapped. A large number of experiments were performed on this kind of with this kind of arrangement, and the first three figures refer to the stainless steel, whereas the last three figures refer to the titanium. Because of the pulse and the line overlap, you can see that variety of linear structures are produced on this surfaces, and when you have a very high pulse as well as the line overlap, then you can get very fine structures. If you can see in this set, you will find that the structures are becoming more or less uniform. Though there are large bursts on this stainless steel, this kind of large bursts are not evident on the titanium, but because of the pulse and the line overlap, you have different kinds of microstructures which are created. If you see the surface roughness, you will find that a greater surface roughness is produced on the stainless steel samples compared to the titanium because of their inherent strengths. However, you will find that because of the greater roughness, these materials have these close to super hydrophobic. These surfaces have close to super hydrophobic characteristics with the contact angle varying between the 143 to 156 on this stainless steel, because the roughness being quite a large and sort of non-uniform or randomly distributed. At the same time, the oxidation levels on the surfaces are very high, so they are a possibility of corrosion. So you need to protect the surfaces. Going in little more details on the profiles of the surfaces generated. So you can see that at higher fluence, very sharp and deep profiles are created on both the surfaces. Whereas when the fluence goes down, the energy density goes down, you find that the surface generated the sharpness is considerably reduced. So this variation is in the order of 5 to 10 micrometers. So this gives some kind of pictures of on one side it is the line overlap, the other side it is the pulse overlap. So the pulse overlap is along one line, and the line overlap is one line is overlapping on the other line, something like side by side, and these pictures are here. So when you make a pulse overlap, larger pulse overlap and less line overlap, then you have a regular line linear features. But you go to the extremity of where the pulse overlap is higher as well as the line overlap is highest, you get some kind of nanostructures here. So these are the randomly distributed nanostructures on these surfaces. Again, as I mentioned, the contact angle decreases because of the on the stainless steel surface, whereas on the titanium surface, again, the contact angle also decreases with the line overlap, the contact angle decreases, whereas with the pulse overlap, the contact angle increases. So when you do pulse overlap one after another, then you have a larger roughness. But when you do line overlaps, one line is overlapped with the other line, then you have the less roughness on the surface, and that reduces the contact angle. The third type of structure is generated by scanning strategies. You have several scanning strategies, and you perform those scanning multiple times, 1, 2, or 3, or 4 times, or 20 times, and then you generate a variety of structures. So here we have laser-induced periodic structures are created, generally called as LIPS. So you can see that nanoscopic structures are created, and these are the reddish pictures or brownish pictures are pictures of the replicated structures and on PDMS and PU. So these polymeric replications of these nanoscopic structures will help you to develop those polymeric structures on the polymeric substrates. And these polymeric substrates have a large number of properties. So these textures developed can act as a mold, and then these structures can be replicated on the polymeric surfaces. So here it gives some more idea about the periodic structures, but these are not only periodic structures, but on the top of the periodic structures, you find that there are multi-scale, the nanoscale. So microscale structures at the bottom and the nanoscale structures on the top of it. So these are like superimposed one structure over the another structure. So this is again possible by means of the strategy of scanning strategies, that is line and line overlaps, and then multiple scanning on the surface, same surfaces by the lasers, modulating the energies and modulating the pulse intensities, and so you can create the multi-scale structures. You will find that these multi-scale structures have much superior properties compared to the other surfaces. So one of the contact angles, if you see that the contact angles on the multi-scale structures is much higher. So you can see that the multi-scale structures as it is, and then they are replicated on PDMS and PU. Then the replicated structures have much higher hydrophobicity. Also, these structures have a large durability over long time. So you test the durability, you put a droplet and keep it on the surface for longer duration, and then see what happens to the characteristics. So they have a large durability, and droplet sliding, you can see that the droplet is completely like a football sitting on the surface, textured surface. Even if you provide an inclination of 16 degrees to the surface, then also the droplet is completely visible and sitting on the surface and not getting slipped off from the surfaces. So transmittivity of the surfaces is also much better, but the multi-scale surfaces have slightly poorer transmittivity as compared to the LIPS type of these structures. The LIPS type of structures, that the nanometric, singular nanometric structures have far more transmittivity as compared to the multi-scale structures. Anti-biofouling properties were tested by putting bacteria on the surfaces like plane surfaces, lip surfaces, multi-scale surfaces, and the liquid infused multi-scale surfaces. So if you provide some kind of liquid over the in the cavities along the surfaces, then their anti-biofouling properties increase, and they can be extended over longer period of time. So you can see that the replicated structures, PDMS and PU, you find that the number of bacteria retained adhesion after a certain period of time is much smaller, comparatively much smaller. So the multi-scale structures offer a significant anti-biofouling kind of properties. And many of these properties like contact angle or hydrophobicity, anti-biofouling kind of properties, they actually primarily depend on the initial microstructure of the initial texturing of the surfaces. So if you simply test the contact angle, that itself gives you a good idea of whether it will have hydrophobic properties, it will have sliding durability, etc., etc., and so on. But here we have tested anti-biofouling properties. So I would like to conclude saying that various micro, nano, and multi-scale structures have been fabricated using laser application, laser micromachining, and they have a variety of applications, right from the aerospace industries to food packaging industries and so on. So thank you for your attention.
Thank you, Professor Joshi. Your class, we're going to have a break of some 5 minutes and we'll start again. So we'll
Sure.
enjoy a break of 5 minutes now.
Okay, thank you.
All of you can rejoin at 10:45.
Professor Rao, what time do we start?
Yes, we are starting right away. We are starting right away.
Okay, so I'm ready. So let me start.
Yes. Now the next speaker is H.S. Kim. Is a professor, Department of Material Science and Engineering at Pohang University of Science and Technology, which is known as POSTECH. He will be presenting metal additive manufacturing for heterogeneous architectural materials. I invite H.S. Kim to start his presentation.
Okay, let me share the presentation. Okay, you can see it.
Yeah,
Okay,
fine.
thank you, Mr. Chairman, Professor Rao, for your kind introduction. Hello, everyone, audience. I'm Hyun Kim of POSTECH. It's my great honor and pleasure to be here and to give my talk in the first Korea-India workshop on what's new in aerospace engineering and materials. The title of my presentation is Metal Additive Manufacturing for Heterogeneous Architectural Materials. I highlight three keywords in yellow: MAM, Metal Additive Manufacturing, Hetero, and Architecture. So let me explain and discuss these three topics as follows. So first, what's heteroarchitectural materials and how we can make it using MAM, and how we can control the nanostructures and microstructures of MAM process material for how high performance. So we are now in the state of the fourth industrial revolution, or Industry 4.0, based on digital technology. There are 10 technological pillars in Industry 4.0, and 3D printing is one of them. In addition, according to the MIT Technology Review, metal 3D printing is the first in the list of 10 breakthrough technology in 2018. So metal 3D printing, officially metal additive manufacturing, MAM, is getting great attention in most of the manufacturing and application industries, including aerospace. That's why we are here today in section 3, additive manufacturing for aerospace industry. This slide is as plot, we call it, showing the material's position in multifunction axis. For example, density versus Young's modulus. Most of the natural and artificial materials have a similar trend in line of various properties. In this case, heavy metals have high Young's modulus and vice versa. So there are big holes which cannot be achieved in single materials. For 3 properties plot, the hole is bigger. So we need to develop multifunctional materials filling this hole. A single material cannot do that. To overcome this limitation of single materials, Professor HCB proposed so-called architectural materials, shortly ArchiMat. It's composed of multi-materials with 5 geometry families. Interestingly, empty space as well as the real material is regarded as a component of ArchiMat. I made these 2 ArchiMats in my lab. First is spiral interlock structure using high precipitation. And this is hierarchical honeycomb or cellular materials with the self-similarity, that is fractal, using multiple stage bundle wire drawing. This hexagon, this big hexagon is small hexagon, this small hexagon. This black one is empty, so this is very lightweight. The second keyword, the well-known heterostructured material, such as harmonic materials, dual phase materials, layered materials, gradient materials, and inverse gradient materials, can produce high-performance mechanical and functional properties, like this. So, heterostructured materials are the future of metallic materials, I insist, considering superior mechanical properties compared to past and present homogeneous materials. Therefore, combination of the microstructural heterogeneity and this macroscopic heterogeneity can be optimum tailored metallic materials. That is, high performance can be achieved by heterostructuring, and multifunctional filling the hole in the SV plot can be achieved by architecturing. By combining these two concepts, hetero microstructures and macro architecturing, the hetero architecture with tailored extreme performance can be achieved. Then how can we produce these Archimedes? It's a problem. So classical processes can hardly make them. But the amazing technology of metal 3D printing have a huge degree of freedom in single in-shape design. So it's explosively growing from fundamental, the number of publications per year, and to application and markets is explosive decreasing. And I have two metal 3D printing machines in my lab. The first one is DED, direct energy deposition type instead this Korean machine. Unique feature of this machine is we have 6 powder feeders, and this is the SLM, selector laser melting type GE, General Electric Active M2 concept laser machine. With this DED machine, we can build layered, gradient, or in-situ alloy because there are many feeding different materials. So heteromaterial can be built using this one. But today's my presentation results are from these samples processed by SLM in PBF, powder bed fusion type processes. And for the best performance of MAM Archimedes, we need to understand the relationship between processing structural properties. Processing structural properties is called PSP linkage. It's very complicated, but we need to understand it. For the heterostructuring, at present, a powder metallurgy process for harmonic structural material and severe flux formation process for surface gradient materials are widely used. Here, but the control parameters are very limited. Only grain size, grain size distribution, and alignment, and rotation, and something like that. But MAM has much more controllable variables and features from nano to micro to macro, like this. Hence, we have much wider window, not only the shape design, but also the material properties. And one unique feature of the MAM process materials is nanoscale heterogeneity. It's called cell boundaries and cell structures. It's different from casting structures. Interestingly, cell boundaries are composed of high distance density, very high, 1 order of magnitude higher than this general casting structures, and very high solid cell ligation. This cell boundary hinders the dislocation glide very efficiently, but not as strong as grain boundary. And this cell boundary increases the strain hardening, elongation, and strength eventually. For utilizing this unique feature of the MAM process material, is cell structures, element segregation cell, we use high entropy alloys having many elements. So many elements can be segregated in the cell wall easily. So what is high entropy alloys? High entropy alloys are defined by multifunctional single phase crystalline alloys with more than 5 elements of equimolar compositions. This configuration entropy S is higher than 1 point R. That's the definition of high entropy alloys. It's less in between 1 R and 1 point R is called medium entropy alloys. R is gas constant. Due to the very high entropy effect, configuration entropy effect, single phase is stable following the thermodynamics. HA has very good powder and liquid flow properties because it's low melting temperatures, it's multi-materials, and it's very wide single phase region. So these two characteristics low melting temperature and wide single phase range are ideal for additive manufacturing. Plus, various elements can induce cell boundary segregation that results in superior mechanical properties in AM parts. So high entropy alloys are excellent candidates for additive manufacturing material. So this slide shows the typical EBSD OIM at various directions. Z direction is the building direction. And well-developed cell structures here. Look at this scale is 2 micrometers. So 1 grain is much bigger than these cell structures. So we prepared high entropy alloy and carbon-added high entropy alloys and carbon molybdenum-added high entropy alloys for playing with the cell structure engineering and segregation engineering. So this figure shows the stress strain curves with the various cobalt, chrome, Fe, nickel, mangan, high entropy alloys. It's called Kanpur alloy. The high entropy alloy and carbon-added high entropy alloy, just cast one, shows very typical low strength, in particular low yielding strength, and very high elongation, over 40–50%. The SLM flow processed high entropy alloy shows very high yield strength compared with that just cast one, and low elongation compared to the low cast one. But this low elongation is still very good enough for structural part applications. This number with 200 for 600 represent the laser scanning speed, millimeter per second. The SLM process 1% added high entropy alloy exhibit even higher strength and better ductility, better than is without carbon. 200 millimeter per second, very slow scanning, produced more coarse carbide, so strength is high, but ductility is low. This superior mechanical properties combination of good combination of strength and ductility, this banana curves, is the in the SU plot is due to the fine cell structures and nanocarbide in the cell walls for carbon containing high entropy alloys. And it's well known that for conventional materials, conventional process carbon added high entropy alloys produce coarse grain interior carbide. There are many inside carbide and very coarse. That results in the reduced ductility. It's not shown here. But on the other hand, as you can see here, the SLM process carbon added high entropy alloy produce cell wall nanocarbide. This black one is nanocarbide. It's only in cell wall and grain boundary as well, which effectively block dislocation glide, enhancing strain hardening, uniform elongation, density, and finally, ultimate tensile strength. So in order to more strengthen the cell boundary and eventually strengthen the additive manufacturing material, I added molybdenum in addition to carbon. These three curves show that Kanpur alloy without carbon is all additive manufacturing ones. And carbon-added high entropy alloy and carbon and molybdenum-added high entropy alloys. The C added high entropy alloy exhibited the best yield strength, similar to yield strength, but higher strain hardening and higher uniform elongation and high ultimate tensile strength, and finally high ductility. So why is that good? So in order to find the reason, we perform the LUR test, loading, unloading, reloading test to measure the backstress here. So we can measure backstress and forward stress, effective stress, like this. So backstress this is LUR test to measure the effective stress. So backstress is the reason for the high heterodeformation induced strengthening. It's called HDI strengthening due to the high backstress. The backstress high strength is higher in molybdenum added high entropy alloys than the only carbon added high entropy alloys. So we can see many this in this EBS here. G and D, geometric nested dislocation, is blue and yellow color in this EBSD, and near this G and D reside in near cell wall in TKD. It's not shown here, but transmission Kikuchi diffraction analysis can show much smaller. This is a TM based one, much smaller geometric nested dislocation like this. The microstructure and HDI strengthening mechanism based quantum model, considering G and D, geometrical nested dislocation, is the source of back stress and HDI strengthening, and this is for forward strengthening, as well as the SSD was developed. And this quantum model was implemented into the finite element modeling. There's very clear anisotropic behavior experimentally and simulation as well, and could be reproduced by the finite element simulation and analyzed. This X direction and Y direction and Z, this building direction properties are very different. It shows very anisotropic behavior. We also consider this crystal plasticity, but we found that this macroscopic anisotropy is the source of this mechanical property anisotropy. Now we are working on multi-scale and multi-physics modeling for optimized topology architecturing, macroscopy architecturing, and microstructure and properties. This macroscopic topology optimization, this is the mesoscopic heterostructure modeling, and microscopic microstructure evolution, and crystal plastic model, and this nanoscale, and nanoscopic molecular dynamics, and phenomenological dislocation kinetics modeling are being done. This is multi-scale and multi-physics modeling. So with this approach, combining experimental work and modeling and simulation, considering microstructure and deformation mechanisms, unique in high entropy alloys and manufactured metallic materials, we are expecting numerous applications of heterostructured MAM materials. So it is in aerospace, in medical and transportation and defense industries. So we hope we can develop the bright future using this material and these amazing processes. Thank you very much, Hyoun, for your kind attention. Thank you.
Thank you, Professor Kim.
Mm-hmm.
We'll move to the next presentation. That will be by Professor Satyam Suhas from Indian Institute of Science, Bangalore. Satyam Suhas is currently the chairman of Department of Materials Engineering at Indian Institute of Science, Bangalore. Today, he will be talking to us on additive manufacturing of materials for high temperature applications. I invite Professor Satyam Suhas to present his lecture.
Thank you, Professor Rao. Good morning to all. In the next 20 minutes, I am going to tell something about the additive manufacturing activities, that we are doing in our lab. And it's nice to talk after Professor Kim, whom I know so well for so many years from our severe plastic deformation days. So it's nice. In the next few minutes, we will see how convergent are our research areas, even in the new field. So this work is done primarily the work that I'm going to present is done by my PhD student, R.J. Vikram. And there are lots of collaborators here. I'm just going to give a snapshot of all the activities that we are doing in our lab now. So Yeah. So I think this slide is now no more important after listening to such a nice elaborate presentation on additive manufacturing. But in one word, I would say that additive manufacturing is a core requirement of aerospace and space sectors, where there are many small components are integrated into one system. And this was a big challenge earlier because the components were fabricated at various places, and to join them and to have a perfect integrity and performance was a challenge. Now additive manufacturing, once applied to these systems, will make all these possible, so that many small components can be integrated into big ones. And of course, the components which are very difficult to fabricate, like turbines, the entire design of turbine, which I'm showing in a short while, has been a challenge for manufacturer even till date, even though the matured manufacturers keep on finding and reinventing the designs. So we are going to tell how additive manufacturing is going to help in these sectors. So main thing which I would like to say here is aerospace sector has particularly paid a lot of attention to this, because the number of processing steps are reduced, weight saving is there, fuel efficiency is there, there is expanded function and application, lead time is less, and life cycle costs are less. But there are issues as well. It's not so straightforward always. Like there are design complexities. Therefore, since the complex designs are there, and these are components which require proper scrutiny after they are manufactured because of their high risk levels. So the post-process inspection is very important. And destructive inspection and certification could be costly, because here we integrate one component as a whole instead of several subsystems. So these are the flip side of that. And then for repair applications, destructive testing is not possible. And again, the qualification of these components as per their airworthiness criteria is very difficult. As of now, there has been a lot of work, including the work on high entropy alloys, which Professor Kim had just shown. But the main work, or a volume of work on AM, comprises of on aluminum alloy, particularly this particular composition, aluminum, silicon, 10 magnesium. Iron-based alloy have been extensively worked, primarily on tool steels and 316L stainless steel. Nickel-based alloys are the most favorite alloys for additive manufacturing. Inconel 718 is most research material, and attempts are being made, and some successful attempts have been made to make CM247, which is the advanced nickel-based super alloy. And titanium alloy, Ti64, is the most extensively researched AM material so far. And then, of course, the attempts are made for refractory alloy, niobium-based alloy, and moly alloy, just we have seen in the previous presentation. So now I'm going to show some of the results that we have done in our own laboratory on Inconel 718. It's a very important material. It's widely used in aero engines, and that require, in the components that require strength up to 650 degrees. And the strength is contributed by the gamma double prime precipitates. And here we have the design shows the entire turbine section here. And here the components where we have been the components indicated here, they can be used by, there Inconel 718 is used. About in the jet engines, about 45% of the engine components are made of Inconel 718. That is a very special material for that. And of course, the additive manufacturing is also used for repair works. And this also has been used very extensively for General Electric engines, so which is shown in the right side of this slide, where degradation of turbine blade, how the blade wear has appeared, and this whole thing can be repaired by additive manufacturing technologies. The temperature requirements are varied for different components of the turbine. gas turbine engine, and then therefore, but one can see that the maximum temperature is up to 650s, and up to which Inconel 718 qualifies quite well for operating in under these conditions. Now, the main problem is related to the manufacturing of these components. Porosity is a very, very important negative attribute to this process, because these are mainly powder-based processes, and all these powder-based processes are associated with some amount of residual porosities. So research is always carried out first to optimize the porosity levels, and then here in this slide I am showing the laser energy versus laser scan speed. Both are two different types of variables, and we can see that if we increase one, it will increase cost, but again reduce porosity. Another case, it will increase the efficiency. But what we need is optimization of both, so that we can have efficient production of defect-free components. Most important for material scientists in additive manufacturing is microstructural control. And we can see that in Inconel 718, which is such a age-old material being used for almost 50 years from now in aero engines, there is a subtle microstructural differences than the conventional cast, wrought, and additively manufactured material, as so clearly mentioned in Professor Kim's talk, that these segregations are very common features of additively manufactured materials, and these segregations also lead to some amount of precipitate stability, and all these things have to be handled. Plus, the proper general microstructural morphology has to be addressed in this case, and then this leads to a very precise control of parameters. So we carried out, so now which process is the most suitable one? Because there are several processes of additive manufacturing now. Which one is the better one? So we made some initial investigation. We got Inconel 718 by electron beam melting methods and selected laser melting methods. And we almost optimized the parameters in both the cases to the best possible density, whatever was available, and with those variation of parameters, and we could make these materials, and these are the results shown on the best output of these materials. So we could see there is subtle difference between EBM and SLM. So microstructures are characteristics of the cooling rates that are encountered during the processes, but in both the cases we have the cell structure being more pronounced in the case of selective laser melting, and the microstructure is more lamellar type. Melt pool boundaries are more pertinent in the case of selective laser melting process than in the case of EBM process. EBM is a very important process because EBM we can keep the substrate at a higher temperature generally, and then this leads to a very, very precise control on the microstructural features by controlling the cooling rate. We can do it. These superalloys are also associated with lots of precipitate phases, which are really their inherent attributes. And each of these processes have different range of phase stability, precipitate stability that needs to be taken care. Now, so in the as printed structure, we realize that the properties are not as appropriate as expected in as built condition. So what one has to do, and microstructure was also not good, so one has to apply heat treatments which are anyway given to Inconel 718 even in the rod condition and cast conditions. So we realized that we need to apply a modified heat treatment strategies for the dissolution of certain precipitates like delta phase, gamma double prime, gamma prime. Considering all these parameters, we have to design a heat treatment strategies, and we indeed carried out for both these SLM and EBM materials, and we could see the property differences and property stabilization for all these conditions. So Microstructural features are also very characteristic. I will, in the next few slides, I will show the very important aspect of it. So microstructures in EBM conditions are generally having one kind of orientation. We work quite a lot on textures, so we all know that the orientations are very important. And for EBM cases, we were able to stabilize certain type of orientations compared to the SLM. SLM was a little more random in this case, even after the heat treatments. Now, in the text, in considering the texture evolution of these processes, now we have seen that in EBM condition we get perfect cube texture, and this paves a way for a very, very important thing. One thing is the most important aspect of it is the precipitate segregation at a grain boundary, as we have seen here. But most important aspect is to get to see the possibility of going towards a similar feature as single crystal or directional solidification type. So we could see here, I will show you this in a short while, how this has helped us. And of course, the heat treatment leads to similar heat treatment leads to different kinds of phase stabilities in this condition. Evaluating mechanical properties, we have realized that we have differences in heat treated conditions of both these materials from their as printed counterparts. So adequate heat treatment is a necessity for each of these processes separately. So no common thing can be prescribed for both. And we have seen a very subtle differences in terms of heat treatment conditions also. I'm not going into detail, and these heat treatment conditions have to be optimized based on the stability of precipitates, as we have done in this case. Because also there is a subtle difference that the bottom layer undergoes multiple heat treatment than the top layer by the time it is built. So this variable has to be taken into account. Now, as I said, there is a secret behind this EBM. The success of EBM process is you can generate, because a very common type of texture is formed, we can generate some kind of a single crystal type of structure by EBM process, which is again another attribute of all these gas turbine materials, right? Particularly for blades which are used in a single crystalline conditions, because we can generate by controlling the cooling conditions, which are much better control in this case. We can very well control the orientation of these materials. So we have carried out this whole thing, and this has paved the way. This is a result taken from Professor Caroline Conner's paper. And then she has shown that by EBM for Inconel 718, she has been able to get a single crystalline structure. So this is one thing that one can do it. And now the attempts are underway to even convert CM247 into CMX4 type of alloys, right? So there are multiple opportunities to develop super alloys with EBM related processes. And of course, gamma titanium aluminide, which always appear and get disappeared because of their poor fabricability. Here we are having an opportunity to optimize the process and make engine of gamma titanium aluminides, because the poor plasticity, which is impeding factor for fabrication, is no more an issue for gamma titanium aluminide. Only thing is microstructural control, property control is the important thing. Heat treatment, just in a few minutes, I will tell how the heat treatments are important, even for Ti-6-4, which is another material which is used in cold section of aero engine components. So there also heat treatments are to be suitably designed. We have done it, and we have seen that very specially designed heat treatment leads to equiexed microstructure, because as such, because of very fast cooling rates, we get martensitic structure, which has to be converted into equiax structure, and that requires a very subtle kind of specially designed heat treatment. That gives lots of opportunities for metallurgists to play around with additive manufacturing process. And property differences in all these cases are also sensitive to direction, the way the things are printed, whether it is vertically built, horizontally built, heat treated, non-heat treated. All these things are very, very important parameters. I'm just showing this. A very important thing that I wanted to bring in is the surface treatment. So we have, as I said, we all started our work with severe plastic deformation. So severe plastic deformation, like surface mechanical attrition treatment, has been found very effective for enhancing the properties of Ti-6-4 because it closes the surface porosity, generates compressive residual stresses, and eventually leads to the very, very optimal fatigue life of these components. Residual stresses, we can see that just by doing this post-processing, it totally changes from tensile to compressive nature, and its attributes are seen in all the properties. Fatigue life is substantially enhanced. The fracture mode is changed by this process. So what I mean to say is very newly and innovative post-processing treatments have to be invented for the entire range of materials in this case. Now, just before I close it, I just wanted to give a glimpse of our work on high entropy alloys, because the tone was set by Professor Kim in the previous presentation. We worked on eutectic high temperature, high entropy alloys, which are supposed to be a potential candidate for replacing some of the super alloys that we have mentioned. And we indeed worked on this so well-established high entropy alloy, aluminum, copper, chromium, iron, and nickel 2.1. And we did this by additive manufacturing, by following all these methods. And because of the process attributes, we got this lamellar plus dendritic structure in a eutectic form. We carried out thorough characterization of this, and we could stabilize the BCC phase and L12 ordered phase and BCC disordered phase as a result of additive manufacturing, which was slightly different from what it is generally made by casting route. So in that case, the FCC phase is disordered and BCC phase is in B2, but as additively manufactured material has ordered FCC and disordered BCC phase. Right, we carried out the interfaces. We could see the absence of diffused interface in between the both the cases by atom probe analysis, and we could ensure that there was no additional phase formation. The phases were only L12 and BCC there. These materials have shown very nice properties at higher temperatures. The strength increases up to 600 degrees, generally up to 600 degrees it can be used. So the strength increases with temperature, and then it substantially, then it decreases. So that sets, for particular this composition, it sets the temperature range of operation for this material, right? We could also examine the orientation relationship in these alloys. And we could see that, there is a chaos orientation relationship between these two phases initially present in the material. We examined the creep behavior, and we could see the nature of creep mechanisms at 600 and 700 degrees in these conditions. And we also carried out post-deformation creep analysis, and we could see that there was a weak texture formed, gas relationship weakens, and L12 one phase develops a very strong texture in this case. So the way forward in this area is we need to develop new high entropy alloys, which can be used as substitute for super alloys, and as well as beyond super alloys, because by additive manufacturing process, we have a window of opportunity to do a lot of alloying additions and generate components and test them, and so that they are more suitable property wise, they are better off than existing materials. So with this, I complete my talk. I acknowledge all my students, collaborators, funding agencies. Thank you very much.
Thank you, Professor Satyam, for a beautiful presentation. We'll come back to you for discussion session later. Right. Now we invite Professor Lee, Senior Researcher, Head of Small Launcher Team, Future Launcher R&D Program Office of Korea Aerospace Research Institute, to present his paper on embracing digital transformation of rocket technology with additive manufacturing. Dr. Lee, I invite you to present your
Yes,
paper.
I just got disconnected. Hopefully you can hear me well.
Yeah.
Okay,
No
thank you.
problem.
Okay, good afternoon and good morning. My name is Kiju Lee, a senior researcher with Korea Aerospace Research Institute. I am responsible for developing preceding technologies for a small set dedicated launch vehicle. Today, I'd like to talk about how we've started embracing digital transformation of rocket business with additive manufacturing, especially with a focus on faster innovation and complex design implementation. So a great example of this in rocket industry would be an additively manufactured rocket engine, which I'm going to cover details later in this talk. Okay, first, I'm going to briefly introduce two ongoing R&D activities of Future Launcher R&D Program Office.
Dr. Lee,
Yes.
your presentation is not sharp. We're not able to see properly the lettering on your slides. It is diffused slightly. Can you?
Let me share it again. Oh. How about now? Is it better?
This is better.
Okay, sorry. So I guess I talked about this page already. So sorry, I have a little bit of a problems with the connection. So if you could bear with me. Okay.
Oh, now again it is diffused.
Okay. So first, I'm going to briefly introduce two ongoing R&D activities of Future Launcher R&D Program Office, where I work.
Dr. Lee.
Okay. Yes.
Still, this slide is diffused. Only the title slide was better. Able to see anything. Our letters are diffused. All the letters are diffused. Figures are, in sort of.
Okay. Sorry, this is what I have, but I will try my best to present in voice, if you don't mind. I only have 20 minutes, so I don't know what happens, but if you don't mind, I will just go ahead and sorry. Let me see. I'm just doing
Can you transfer your file to Korean office? EK, they can as well try to project from there.
let me try to. Oh, that's just not possible then. That's interesting. What can I do? You can see me. Can you see me?
You go on this mode.
If you, Dr.
present.
Lee,
Yes.
if you can make it a PDF file, then also it could be okay, and show, then the problem may not come.
Yeah, I have a PDF file I already sent to.
If you can share that, it could be better, I believe.
Yeah, I think it's already shared, right? So
instead of PPT file, instead of PPT, you can show PDF.
Okay.
That may not create a problem.
I think the headquarters is sharing the screen already for me, so I'll just go ahead and present. Sorry for the inconvenience, and I don't know what happened. Can you actually see the? I have no control over the screen here. Oh, this is so awful. Okay. What can I do? 네. 여보세요?
Yes, this is slightly better. This is slightly better. Okay. Proceed. Proceed.
하시면 될 것 같습니다. 잘 보입니다. Let's go ahead.
Next, please. So I'm going to, this time again, briefly introduce two ongoing R&D activities of Future Launcher R&D Program Office. One is for two-stage, two-orbit upper stage development. I'm introducing this first, even though we are talking about additive manufacturing here, because we are a group of engineers that work on rockets, not 3D printing technology itself. But we are all for 3D printing, and 3D printing is a great technology for some components in rocket industry. But quite honestly and realistically, not more than 10% of our parts are going to be additively manufactured anytime soon. Nominal mission of our two-stage to orbit is to inject 500 kilogram to 500 kilometer low Earth orbit, which requires a new high-performance 3-ton class upper stage engine. And we've been actively developing additively manufactured chamber and turbo pump, as we believe we can get the greatest value out of additive manufacturing in these parts. In addition, we are investigating the applicability of 3D printing as we carry out conceptual design in many different subsystems. Next, please. In another project of Future Launcher R&D Program Office, we are developing vertically takeoff, vertically landing operation platform, as shown in the leftmost figures, where we need a landing engine capable of deep throttling, meaning controlling the thrust level for soft landing. This is key to overall success of the demonstrator vehicle. We found a lot of advantage in using 3D printing, as it allows us to implement an innovative combustion chamber design at a faster speed than ever. For example, our team member came up with a great idea of having both liquid oxygen cooling channel and liquid methane cooling channel in an alternate fashion, instead of using liquid methane only as a coolant, which is probably hard to build even a prototype in a traditional sense, as the design cannot be easily verified and it may require several costly and iterative processes. Next, please. So we've been developing a 3-ton class liquid oxygen and liquid methane rocket engine shown in the middle, which is composed of combustion chamber, turbo pump, nozzle extension, and engine control units, including valves and pipes. It's actually not that small in physical sense. I was going to show me standing next to the engine. It's a bit taller than myself, but it's quite small in terms of thrust force level. Okay, so we find the immediate value of and interest of developing this small size engine with additive manufacturing, as it will be used for upper stage of the two-stage to orbit I mentioned before. Once developed, this engine would become even more valuable, as it can be adapted to many future vehicles, including space tug, lunar lander, and space plane. Next, please. Okay, we strongly believe that combustion chamber, shown in the center, is the engine component that can get us the greatest value out of additive manufacturing. The combustion chamber is composed of mixing head at the top and regeneratively cooled cylinder and nozzle section below the mixing head, which is a very complex internal structure, meaning that it requires a lengthy process of machining and welding if we use traditional manufacturing method. By introducing additive manufacturing, where you can selectively melt powder in a bed layer by layer, we can design and build an integrated mixing head as a single component. We can not only reduce the number of parts significantly, but also shorten the manufacturing process from 6 months to 1 year to 2 to 4 weeks. Of course, this is only true if the printing recipes are tested out and held in your hands. Okay, depending upon the available printer size, in the best case scenario, a 2-piece combustion chamber body can be built, as shown in the bottom right. A US company called Launcher is indeed building this 1-piece chamber body using a large-scale metal printer that allows a build height of 1.5 meters. Unfortunately, this printer and metal powder associated with it is not yet available in Korea. Next page, please. I just can't think of a single rocket company that doesn't want to use the 3D printing engine, because it's actually a very good idea. However, 3D printing is not a magic solution. Some parts are designed to be 3D printed, other parts are designed to be machined. Engineers are looking at this and deciding where 3D printing is worth trying. Honestly, I don't know if a single 3D printed part that doesn't need a little bit of machining afterwards, because some surface where you have a seal, for example, need to be in high tolerance. As engineers, we need to make the choice, considering the strengths and weakness of 3D printing as described in this table. I believe we can achieve higher performance as AEM technology allows for faster and more iterative development cycle. I'm going to talk about this a little more. Also, budget permitting, we can simply bring in more printers for high production rate. In Europe, they are developing 100-ton class locksmithing engine, so big engine with additive manufacturing, and their target is to reduce the engine price to 1/10. For us, we designed and built a 1-piece mixing head with a bundle of feed lines as shown in the bottom right, which is supposed to provide uniform flow into a number of injectors we have in the cylinder section. On the other hand, 3D printing still needs to be diversified powder material, standardized process for quality and repeatability, as well as overcome the size limit. Next, please. Since 2020, when we actually initiated our project, we've decided to take in additive manufacturing for more engine components, including the combustion chamber I just mentioned, several turbo pump components, and valve housing as shown in the right-hand side. The metal PBF, which stands for powder bed fusion, especially SLM, selective laser melting, has been extensively tested out using Inconel 718, as discussed before, and copper alloy. Next, please. Unfortunately, I cannot share the video, but anyway, for combustion chamber, we used metal 3D printers of 2 different sizes, okay, depending upon the component dimensions, of course. For example, the cylinder part in the middle requires a printer that provides a build height of a 400 millimeter approximately, while the head and nozzle can be printed out using a smaller printer version. Also, you can notice that sometimes they use more than one laser to speed up the building process as shown in the middle. In case you are not familiar with combustion chamber, you may think the cylinder and nozzle do not have a complex shape. They are mostly symmetric. They actually have internal channels to cool down the inner wall of a combustion chamber, which makes it extremely hard to manufacture in a traditional way. I'm going to show you the channel in the next slide. Okay, so the bottom right shows the nozzle part sitting on top of the build plate, where you can actually notice support structures that are needed during the build. Without heat treatment, there's a lot of stress in the printed part. We typically wire cut the printed part after the heat treatment. I actually didn't know much about the audience, so maybe some parts of my talk is very fundamental. Okay, basic. I mean, next, please. Next page. Okay. We use modeling and simulation throughout the whole process of 3D printing. For example, a process simulation is carried out to define laser sequence for each layer to minimize stress concentration as much as possible, and to design the temporary support structure I mentioned in the previous slide during the build. Subsequently, distortion analysis is conducted to identify the local features where thermal distortion can be more than pre-assigned value. So in a nutshell, we must modify the original 3D model into 3D printable one. With this updated model, we build these local features prior to hitting the go button for the whole component, because we think if the most complicated design is free of issues, then the part is likely to have no major issues. One of the toughest requirements we had was to build the inner wall thickness with 0.3 millimeter plus minus 10% in a consistent manner throughout the whole component. Okay, you might be able to see a little channel in the photograph. I was going to zoom in, but I don't have that here. So next, please. Okay. In general, we are extremely careful about adopting new technologies in rocketry. At least that has been the culture before the emergence of new space companies like SpaceX. Some people still don't believe in 3D printed rocket engine, even though company like Rocket Lab has demonstrated this many, many times. It's no different in Korea. So we decided to go with a smaller scale combustion chamber and wanted to show that it can be done quickly. It took about less than a year for us to design, build, and test this 3D printed combustion chamber. It was even more challenging because we had to develop the test instrumentation that can use a new combination in Korea of a propellants, liquid oxygen and liquid methane. Next, please. Yeah, I was supposed to show the video of a hot firing test. Okay, so basically it's a 10-second hot firing test we conducted this month, a few weeks ago. Actually, the last week. We disassembled the combustion chamber made in copper alloy after the test and found the internal channel and injectors are in good conditions. Well, also we plan to increase the burn time in an incremental manner and analyze performance data. Subsequently, we will switch to the mixing head design number 2 that has slightly different design of injectors. I think this kind of fast design iteration is only possible because we use 3D printing. Next, please. So I would like to touch upon how we are using additive manufacturing to implement a novel idea into a product. We typically use fuel only, in our case, methane, to cool down the chamber body. If you decrease the thrust for landing, for example, the mass flow of methane becomes not enough to cool down the chamber body. So the idea is to use both liquid oxygen and liquid methane to cool down the chamber body in order to have enough mass flow. We just need to build an alternating channel for this, which is, I think, nearly unthinkable if you don't use additive manufacturing. So we plan to demonstrate the deep throttling capability by hot firing test later this year. Next, please. Okay, so switching gears, I'd like to touch upon the 3D printed propellant tank we built in collaboration with our colleagues at KeyTech 3D Printing Center. A directed energy deposition process, which is called DED, was used to build a common bulkhead tank as shown. So strength tests as well as leak tests have been successfully conducted. We decided to use powder-based DED and STS316L, as these are the only workable options within our budget and time limits. A US company called Relatively Space is known to use wire-based DED to build a much larger tank. Unfortunately, this is not yet available in Korea. Next, please. Okay, so we plan to extend the DED process to high pressure tanks for upper stage application, where we intend to develop a functionally graded DED process where titanium or Inconel 718 and STS 316L meet at the poles. In addition, we are interested in developing a 3D process that uses aluminum alloy for a sizable upper stage tank, where the caterpillar shaped tank is desirable for maximum capacity within a given volume. This is more of a future work we're interested in. Next, please. Another interesting area of research is to carry out the topology optimization and to actually materialize it using additive manufacturing. For example, we started with a typical engine thrust frame shown at the top, which is already optimized for machine version. A topology optimization resulted in a cell-based complex design that is shown right below. We were able to reduce the weight by 30% in this case. We also plan to use additive manufacturing for curved pipe manufacturing. I just mentioned that here. Next, please. I would like to summarize. Slowly, maybe, we've started embracing digital transformation of rocket technology with additive manufacturing, especially with a focus on faster innovation and complexity design implementation. In my humble opinion, we still need to diversify source material, standardize the AM process and framework for quality and repeatability, as well as overcome the size limit before the business of building rocket components using additive manufacturing can be put into practice. Thank you very much for your attention. Sorry for the video situation.
Thank you, Dr. Lee. You have presented very well in spite of initial hiccups. There's no problem. You have completed within time. Thank you very much.
Thank you.
Now, we had 6 presentations in this session, and we'll have a question answer session now. Elaborate discussion we can have on the papers that have been presented. Let me check in the chat box where there are any questions today. There are no questions that have been put in the chat box, but we can have some discussion. Speakers themselves can raise the questions to others. Okay. 6 speakers can mutually raise the questions to get some sort of clarifications from the presentations. Can I start with Sachin Savas?
Yes, yes. It was very nice to listen to the presenters, and as I said, I know Professor Kim so well. So my question to Professor Kim is there any future of doing additive manufacturing of light alloys like magnesium and others? Because there has been a lot of issues with magnesium processing. And I feel if we find a solution for doing additive manufacturing of magnesium alloys, probably lots of these poor plasticity related issues we can solve. So has there been any effort, and is there any experience on your side?
Yes, I know one company in Korean, DED machine company, who can additive manufacture the magnesium powders by strictly controlling the environment. Otherwise, they can explode. It's very dangerous. So, yeah, theoretically, if we can control the atmosphere, then it is possible. So, but yeah, there are some dangerous situations. So, I think that magnesium and magnesium alloy is not impossible. So, that can be the future or lightweight made material. But basically, As manufacturing materials, we can make very lightweight by good topology optimization. So do you want more lightweight? The lighter the better. Yeah, I know.
There are other ways to do that. AM provides a good avenue for making structures lightweight. Yeah.
Okay.
In fact,
I will have one more question, Professor Rao, if I am allowed, or
yes, we'll come back to you again. In all the presentations, we touched upon the source material, that is the feedstock material. What is the type of feedstock material we have to use for aero engine components? Because atomization is the process where the powders are being produced. Other one is the prep process where the powders are being produced, which will be giving the better result. I seek clarification from the speaker from Hanwha Aerospace Center.
Yep. I'm sorry, I cannot catch your questions directly. Once more against, please questions one more time.
Hello. Hello.
I'm sorry. I cannot catch exactly your questions.
Yes.
Please one more.
Yeah, anyone can answer. No problem. Anyone can answer. Which is the source material that we have to use for getting better properties and to get the better surface finish, the powders, and the powders themselves, may have inherent porosity during production itself. All these things we have to take into account to get a better product with good mechanical properties. So, which is the better powder? Is the prep powder, atomizer powder? Any research has been in this direction?
As you know, the 3D printing, the weakness point is the porosity in the field part. Therefore, we have to generate the mechanical property, especially the fatigue strength for application blade. Therefore, so we have to get the powder from the already approved company, as you know, the carpenters and other special materials. They give us their material property, and then we can get that data for our design data. This is important to us to generate the designer level for applications, the blades. As you said, the porosity is important to us to eliminate the design curves.
You have shown the fatigue design curves for some materials. How does the fatigue properties generated on AM parts would compare with the conventional parts? What is the penalty that AM parts are going to have? How much is the reduction, percentage reduction in property? For example, fatigue or creep.
Oh, no. I cannot remember exactly the deviates from the conventional road railway to the 3D printed part. It is different each material. Therefore, I cannot get exactly the answers from your questions. The different the power of the material, each part.
Yeah, generally we know that surface porosity is more dangerous, but
Yeah.
of the heat treatments or the hot isostatic pressing process also,
Yeah.
we are able to heal some of the lack of fusion defects, which are acting as the crack initiators there. So, is there any way that lack of fusion defects can be minimized by any other process or by any other treatment or something like that?
Yeah, we have the sub-process to eliminate the surface weakness. Therefore, the 3D printing post-process is important to the fatigue strength. As you know, we have to use the polishing is important to eliminate the surface roughness irregularities. Some others we use the high temperatures, isothermal pressures processes used to eliminate the inner porosity. Sometimes it is effective to eliminate the porosity in the inner porosity. Therefore, can get the higher fatigue stresses from the from the 3D printed parts.
Now, people are talking about, it is common to everybody, which Satyam also has presented, the orientation, dependence of the mechanical properties or microstructure.
Mm-hmm.
Somebody will say transverse direction and, longitudinal direction and other thing, and orientation of 45 or 60 degrees or something, which is the most preferable orientation for IN 7 and 8 superline. So this is being used very extensively for aero engine. Hello. Hello.
This
Hello?
question is to whom, Professor?
Satyam, you can answer.
Okay. So I 718 has if you print this material, you will always get very strong and in order to avoid the cube orientation, you have to do a certain processing. So generally, cube orientation is unavoidable and it gives very anisotropic properties that we have seen drastically. So either one has to do some additional heat treatments, but heat treatments also to control cube orientation will be very, very difficult. So we have to, during printing itself, we have another set of investigation where we carried out by changing the printing parameters, including hatch rotation and including laser power combinations. That leads to a minimal of anisotropy. And this has been very well proven in our recent paper on 316L, which also behaves in a very similar way. So one has to actually here texture control becomes very, very difficult because we don't have, normally we control texture by plastic deformation and annealing, but here we don't have avenue to carry out plastic deformation. We produce near net shape parts. So it is just by very subtle combination of parameters during printing itself, one has to control.
The problem of high residual stresses and then conversion of them from tension to compression. That plays a very important role. Tensile residual stresses are not allowed in any of the parts. And then, what are the appropriate measures we have to take during the deposition itself in order to minimize the tensile residual stresses? Any one of you can take up the question and answer. Kim sir, Kim.
Yeah, I have no solution. It's not easy to avoid the tensile residual stress on the top of the built material. So maybe stress relief annealing is the only solution. That's what I'm saying. Then I have one more comments after the Professor Subas. He is the expert in texture. So controlling the crystallization texture is extremely difficult. Deformation texture is easy, relatively easy, but the crystallization or solidification texture is very difficult to control. But we can utilize it because for surface condition, loading conditions are not isotropic. So we don't need to make the material isotropic. So if you know the loading condition, surface condition, one direction is mostly highly tensile, the other solid directions are relatively low stress. Then we need to build the material, that printer, considering that stress condition, the surface condition. That's the easier way to avoid the texture problem, orientation problem. That's what I'm saying. And I want comments, and it's my idea about this surface roughness, surface residual porosity problem. So as Professor Subas mentioned, this surface treatment is a very good way to remove the residual stress and extend the fatigue life. So he used the SMET surface nanocrystallization. It can refine the grain, surface grain to nanocrystalline. And in addition to that, the surface compressive stress is highly generated. It's a very good way to escape the surface fracture or something like that. And as to porosity, so yeah, I know that it's very easy, it's very difficult to remove all the porosity, but if we control the scans, many 3D printing parameters like energy density and scan speed and the width, and we can almost remove them. So in powder metallurgy society, we call it full density if it is over 99%, 99.9%. So if we control the processing parameter well, so we can remove most of the remaining porosities. So one way to remove the unmelted powder, what's the name? I forgot the name. Is the one technique is a double scanning. So after one scanning of the laser in SLM, not ED. So we scan the surface without any powders. Then we can remove almost the unmelted powders. There are several techniques.
Right.
That's it.
We have discussed several high temperature materials, ultra high temperature materials like borates, hafnium borate, zirconium borate, then high very high for very high temperature applications, and then conventional sopralized stainless steels and titanium alloys for aero engine applications and other. Now, what are the difficulties one can face in preparing the high entropy alloys? Do you require the powders of different size, distribution, and all those things? Or can you use the multi-feeding facility for different powders for making the high entropy alloys? Or you require at a time itself, all the powders can be fed and deposited? In which way you suggest pre-alloying or elemental powders? In which way they will give better results, homogeneous product for you without segregation and other things?
Yeah. Again, Professor Kim is the most qualified person to talk about this.
Yeah, it's still not easy to make in situ alloying. So the easiest way to use alloy powders. Then can solve the segregation problems. And I don't have the exact answer. I'm trying to solve it. Yeah, I'm still struggling.
I just would like to add to Professor Kim's point that I think we have done some minor alloying kind of thing, that we get a powder of a certain alloy, maybe a combination of 3 elements, And then we do some, in order to balance the stoichiometry, we have added some additional powders and mix them well and try to print it. In some cases, it was successful, but of course not in very complicated cases. In some cases, like suppose we take nickel, cobalt, and iron, these three powders, if we take, then probably it will be successful because they have many characteristics very similar. So there, if you get iron, nickel, raw powder and alloyed and try to add cobalt through this DED process by properly controlling the feed rate and all that, it could be possible. So I think so that is what one important point that I have put in my comment, that if we have to develop this technique for a full metallurgical landscape, we have to evolve this premix powder route, what in old powder metallurgy we used to call it premix route. So if we are able to do premix, then we have the entire spectrum of materials that we can generate, right? But that requires again a very subtle optimization of parameters for each case. Right? That's all is my submission. Professor Kim.
Yeah, I agree. We also do mechanical alloyed powders. So in that case, yeah, there's almost no problem. But yeah, it takes a long time and not always they're successful. So we want to use the elemental powders to control the final composition. It is the basic route for high entropy alloys. It's the future.
Dr. Lee has presented a beautiful presentation. He gave us details completely with respect to digital transformation of rocket technology by additive manufacturing. The talk is very interesting. He brought out the strengths and weaknesses of 3D printing in producing the parts and their usage. And he said that only 10% parts of rocket can be produced by additive manufacturing technology at present. So he has dealt the research that has been carried out with respect to combustion chamber elaborately. And then he also pointed out there is an urgent need for standardization and repeatability of the properties and as well as the process and other thing. So what are real initiatives that are going on in this direction? Can you little bit elaborate such that everybody would get benefited from your knowledge?
Well, quite honestly, I am not doing any research on standardization. I just we actually built several identical parts, and then turns out it's never the property of these parts are never the same. So that's one weakness because we're going to talk about additive manufacturing today. I just sort of it's a good point to mention, but I'm not really pursuing any research on that track. And what was the other question you had? Sorry.
Now what we are doing is we are making a part, okay, single, yes, and determining its properties, and then trying to establish the design curves for the single part. But in future, from now onwards, within 10 years time or so, that AM technology will go to produce the systems, not the parts. Each system will consist of so many parts. How to integrate the deficiencies, solve out the deficiencies such that system would perform for many years to come. For example, component that is, you are putting inside the aero engine, it should be of high structural integrity, very high structural integrity. So in which direction? What are the ways to produce high quality structural integrity systems?
Okay.
I'll say we are facing so many problems.
Yeah, I was just I was just doing reality check, and the 10% it's actually the number I got from Rocket Lab, which is a small dedicated launch company that is sending small satellites to orbit, and they built engines using additive manufacturing or 3D printing. But that's the first company in our field, and then they're only using 10% of their engine components using additive manufacturing, and then we are slowly building our confidence in using additive manufacturing in high temperature and oxidation of applications in rocketry. But it's never easy to persuade people who cares more about heritage, the old-fashioned way of traditional machining, welding, etc., brazing. So that's why we started build smaller parts, and then maybe incrementally prove that the technology can be available for system level. But for now, in my humble opinion, part level still we're struggling with a standardization of a process. And data. We have a lot of data from 3D modeling to printing, inspection, and etc. But they are not really, they're not really system to feedback that data into our new design or newer design. That's the problem we're having. So, but I don't have the solution in my hands, honestly. Thank you for your question, though. I actually had a question in my chatting window, if you don't mind.
Please carry on. If you have any question, you can pose it.
Sure.
Thank
you.
Just a moment.
Yes.
In my opinions, in the design point, our company also designed the rocket engines. Therefore, the aero engine also, the material property generation to design is important. Therefore, all powder material must have been generated the design data from the powder and the machine and the software collaborations. It is based on the standard base, the quality and the process, and some other material specifications.
Yeah.
If you have any chance to meet our company engineer, I would like to introduce our systems to generate the database for aero engines or the space material also. Thank you.
Thank you. I was actually talking about like the AMST type standardization, not necessarily custom printer and powder material, but for reuse. But anyway, thank you. I will contact you.
Yeah.
Just there are a few questions here in the chat box. How long term durability of additive manufactured components is tested other than creep testing? Durability testing other than creep of additively manufactured parts. Durability in the sense there will be fatigue and all such type of things. How much time they have been tested, for how many cycles they have been tested, like that it is. This is posed by Suhas Joshi or everybody who have presented their papers. Anybody can answer. We know very well that a lot of process parameters and other things are being varied, and then their influence, heat treatment influence, and all those some properties we are getting, microstructural modification we are getting. There are two areas which have been neglected because, for example, today we are discussing the aero engineering, topic, and then aero engine parts, they are subjected to repeated thermal stresses at high temperatures, which will be fatigue oriented. It must be low cycle fatigue, it may be high cycle fatigue, or some sort of, what I can say, variable loading, and all those things will be there. But most important is at high temperatures, one property is there, that is creep. Creep and fatigue interact and cause the much lesser than what it is to be, what you're anticipating. So how much, efforts have been put to study the creep, fatigue, and the environment effects. Environment also plays an important role there. So this is where we do not have much research carried out anywhere. So it needs a lot of attention. When we call about the long-term durability, these problems will be coming. All of you are requested to, participate and try to answer this question posed by Joshi.
Okay, if I give a pointed answer, I can tell that certainly these tests are nowhere compared to the tests that are done for a conventionally produced material by thousands of hours of cyclic loading and all that. So most of these things, whatever to the best of my knowledge, are limited to laboratory results. So maybe some 10 samples would have been produced, and maybe maximum, say, over a period of a few days. But I must add that there is a group that is working on developing ASTM standards for AM materials. So this group, in one of our recent workshops, there is a group from, I think, Sweden, or they were mentioning that there is a very conscious effort being made to type certify these materials. So in those conditions, these parameters will be considered. So as of now, whatever we know, unless GE and other companies who are big, who make a big entry into these fields, they have some database, at least not in open literature. There is any indication that these are tested for a very long time. So far, it's into laboratory range. That's what I understand. But others may know better than me. Thank you.
This is an area we have to pursue in cooperation. To you, there is one question from Lee. He poses a question in the form, in the following form. I am trying to build high pressure tank, pressure 200 bars using GED and functionally graded approach, which is heterogeneous, where titanium has to meet stainless steel 316L, which might not be easy in these sessions. What he says, meeting titanium to 316L, probably joining, probably he must be having mind. Is it true, Lee?
Yes.
Yeah.
Kiju.
Yeah. So anyone can answer this question posed by Lee.
It's not easy, because definitely there will be cracking in between the stainless steel and titanium 64. Because I checked the phase diagram and I found two intermetallics. So definitely in between this and this, they will come across that intermetallics. So we have to consider phase diagram to escape that region. So that's the tip. So if we control the fraction of the two powders and escaping that dangerous area, it will be possible. But you need to try. Even if we escape that exact composition, there is a 3D printing. It is layered one, so there is a diffusion. So there is some interface region. Then having a broad composition that will produce the cracking problem. That's my experience, and all metallurgists know it.
We have come to the last phase of our discussion. There are several people who participated in this program. All of them have not got the opportunity to present their papers. There are several institutes in India who are very active in IT manufacturing. There are some companies and research centers who are very active in AM process, and they have produced some components. Even our space program has produced some components for our rocket engines and other things. So there is one center which is known as ARCI, Advanced Research Center International for Powder Metallurgy and other things. They are very active in producing some of the parts and doing excellent research in additive manufacturing. There is IIT Bombay, IIT Kharagpur, IIT Hyderabad, IISc Bangalore, IIT Delhi, then our Space Research Center, VSSC Trivandrum, and then Defense Metallurgical Research Laboratory, Hyderabad, Gas Turbine Research Establishment at Bangalore. All of them are very active. Many companies are also very active. They are producing the parts, if we give the design to them. 3D printing they are doing and giving us parts, and characterization and everything is going on. What I suggest is that we'll come back to you to have some sort of collaborations between Korean universities, research institutes, and industry, as well as the counterparts in India.
Yeah.
So we'll be discussing that, and we'll have a fruitful collaboration. And some of the points what we discussed, where are the difficulties, how to ensure the integrity of the parts and other things. So the variables that are involved and other things, some of them we can solve, taking some sort of a powder which is common for all, produced by one route of same size and distribution, and processing with the identified parameters and all those things. In some sort of round robin program or something, we have to work it out, and we'll be discussing that one in the evening, and follow-up actions will be taken to establish the cooperation between the universities as well as research institutes and industries. So, thank you very much. I thank personally everybody, the speakers who participated and enlightened all the participants in the current status, giving the current status of additive manufacturing on several materials, both metallic materials, intermetallics, then ceramics, and as well as emerging high entropy alloys. That is very good. Thank you very much.
Yeah.
Thank you.
Thank you very much.
Thank you very much.
Bye bye.
Thank you.
Our INL coordinates with NAEK to establish the operative programs. Thank you very much.
Professor Sankara? Yeah. Professor Sankara, I have a questions to you. We have also some problem to test the thermomechanical fatigue for aerospace engine. Therefore, we would like to get the informations of your country, the specialist or special institute.
Yes, we have some.
Please give me your side, the specialist engineers or others research or professors to give us the information for my email.
I will send you email that who are active in this area. Okay.
Okay.
It's not a problem. So yesterday, Professor Banerjee has highlighted in his talk about some of the activities that are going on gas turbine research program. Okay, so under that program, some machines have been built for mechanical fitting. Then we have at Defense Metallurgical Research Laboratory the active research is going on thermomechanical fatigue. And there is another center which is known as Indira Gandhi Center for Atomic Research. They are very active in TMF activities. And our VSSC space program, which is direct relevance to today's topic what we have. They are also very active in thermomechanical fatigue. So I will come back to you, giving the names of the scientists, and and we'll work out for some cooperative program on this too.
Now I see one expert, Professor Subas he's an expert. Yesterday, Banerjee is also a good professor.
Yes, very nice. We had extended discussion, which is very fruitful to initiate the collaborative programs between India and Korea. And I shall thank both INAE as well as NEEK to organize such a beautiful program, selecting proper speakers for the symposium. Thank you very much.
Thank you very much.
Very much.
Bye-bye.
Bye, Professor.
Bye-bye.
Bye.
Yeah, give my best regards to Atul, Chokshi, and Praveen.
Sure.
Okay, bye-bye. And Professor Ranganathan as well.
Sure.
Okay, the session is closed now.
Thank you.
Thank you very much.